All right, hi everybody. In between two AI talks, we're going to talk about something completely different, which is property-based testing. And before I start the talk, I just want a quick show of hands. Who here really loves to test their code, really loves to write tests for their code? All right, one person, 2 people, 3 people. All right, you're all wrong. So this is why my talk is about getting computers to test your code for you. So when you write code, you want your code to behave the way that you expect it to, right? And for a small project, like, for example, something that you do over the holidays, it's fine if your code has bugs in it, right? Because your code can tolerate bugs. You can work around it. Other people can work around it, whatever. However, if you are writing code for a safety-critical system, you definitely do not want bugs in that code, because a lot of lives or a lot of money could be depending on it. Examples of safety-critical systems? Well, medical life support systems, nuclear reactor control systems, spacecraft command and control systems, and of course, automated trading programs. These all require code, and we're the people who write them. So how do we write them? So let's do a thought experiment. Let's say that you are writing the navigation code for a rocket. You and your friends, right? Just you and your mates. And that rocket is about to blast off, and you're about to board the rocket. Would you trust your code enough to board that rocket? Would you trust your code to save your life? Show of hands. All right, we're pretty unanimous on this one. OK, good. And I think the more important question is, how would you make sure your code covers every possible edge case? So there are a few methods for software safety that we can use to ensure our software is correct. The first one, we could use a language with a type system designed for safety. There are a bunch of languages out there that have really good type systems that allow you to write safe code. You could also use formal verification, which is like a way in which you can use mathematics to prove the correctness of your code. Or we can do testing, and this is going to be our focus in how we can test our code. However, we will get back to these first 2 methods later, because it turns out property-based testing actually complements these other 2 methods really well. So you've all done unit testing before. Well, maybe not the Komskis around here, but actually, no, maybe not the non-Komskis around here. I hope everybody here has done unit testing, even the Part 1As. We're doing OOP right now. Anyway, unit testing is essentially when you write examples of inputs and expected output to test each function you write. And that's good because most of the time, the unit tests you write are small, right? Which means they're easy to debug if something goes wrong. You can also easily tell when your code doesn't output the correct answer, right? Because you have your input and your output, and if your code doesn't produce the correct output, then you know it's wrong. However, as system complexity increases, unit tests become much more time-consuming to write. It's also very easy to miss failing cases from human error, because you're writing these test cases. What if you miss some corner case that you only encounter in the real world? That would be disastrous. And also, I hope the Komskis can agree with me on this, unit tests are kind of boring and brainless to write a lot of the time. Yesterday, I was just copying code for my OOP because I needed to implement like 2 different classes for lists, and I just couldn't be bothered writing separate tests for each of them. So Andrew Rice, if you're watching this, I'm sorry. On the other hand of the spectrum, we have random testing or generative testing. And that basically asks the question, well, why can't we just throw large random cases at our code? Right? That should be able to cover everything. Well, now we have a problem. If we're just throwing large random cases at our code, how would we be able to tell if the code's output was correct? Because we're not writing the outputs anymore. So who's writing the outputs? We introduced property-based testing as a testing method which combines the best of both worlds and helps us write better code. Before I explain what it is, though, I'm just going to talk about the programming language that I'm going to be using for this talk. So most talks and articles on property-based testing use some sort of functional programming language, including the original paper which used Haskell. However, this testing method is not exclusive to functional programming. In fact, quite the opposite. Implementations for property-based testing are available in a lot of languages, including Python. So I'm going to be using Python 3 with the hypothesis package to demonstrate property-based testing. First of all, what is a property-based test? Well, if I was asked to describe it, I would say that it is a test that is meant to programmatically check if a function behaves in a certain way. So what does that mean? That's kind of abstract. Well, let's have an example. Let's say I was writing a function that takes in a list and outputs the elements of the list in reverse, right? So I call it my reverse. And then I notice something about when I reverse a list. And it's that if I reverse a list twice, it's going to give me back the original list. So reverse is an involution, if you will. And so I can write this property down formally. For every possible list of integers, x's, reversing a list twice will always give me back the original list. And so, OK, we can now express this in code. So first of all, I import the hypothesis library, and then I tell it I want lists of integers. And then I write this really simple test that takes in a list of integers and then checks if, when I apply my reverse function to it twice, it's going to be the same as the original list. Now that we have a property, we can begin testing it. So how does it work? Hypothesis will start generating lists of integers to test. And it's just going to keep generating. And after a certain threshold, let's say 100 test cases have passed, it's going to say, OK, I think this test is pretty good. I think your code passes this test. So it's going to move on to the next one. However, what if it finds something that breaks the property? What if an assertion fails? Well, we can just give that code back to the developer, right? We've found a breaking case. So that's what I told Hypothesis to do. I told it to just give me the first failing case that it found for my buggy reverse function. And here it is. It's a bit of a nightmare. You wouldn't want to debug this code. You have like this huge number here. You just have no idea what the problem is when you look at this test case, right? And not only that, if you step through it with a debugger, it's going to take such a long time to notice where exactly your code went wrong. And you might have to step through it a couple of times to figure it out. So large and cumbersome cases are not very helpful for debugging. So how do we deal with them? Well, what if we generate only smaller cases instead? No. Larger cases are more likely to detect bugs in code, right? So we actually do want larger cases to generate, but we only want smaller cases to debug. So we kind of have this trade-off here. But we can observe something from the larger cases that we have. And it is that when we consider the distribution of data in that case that actually causes the bug and the distribution that just does random stuff, it looks something like this. Right? So a very large section is unnecessary fluff, and only a small section actually causes the bug. So what if we could find a way to trim down the fluff and only take the section that actually causes the bug? Well, this is where shrinking comes in. And when we shrink our test case, essentially, what we're doing is we're generating alternate smaller test cases given a large one that's failed. We then run each alternate case against the original function to check if it fails. And as soon as we find one that fails, we use it to generate smaller alternate cases. And we keep doing this, and we keep doing this all the way down until we can't anymore, until all of the alternate cases don't break the code. And when that happens, we stop. And then we just give it back to the original developer, and hopefully it's small enough. So you can think of it kind of like a greedy hill climbing algorithm or a greedy tree search algorithm. Let's start with an example. Let's suppose that the counterexample list was this thing, and it just goes on for an arbitrarily large amount of numbers. And OK, let's tell Hypothesis, I want a counterexample. Give me one. Empty list. Good guess, but it doesn't break the code. All right, list containing 42. All right, you're taking the first element. Yeah, I see what you're doing. Good guess, not breaking the code. All right, you take the first two elements. OK, that does break the code. OK, good. Now, hypothesis, generate me counterexamples for the list 42, 1. Empty list, we've tried that. 42, OK, we've tried that. List containing 1. That doesn't break the code, but good guess. OK, so hypothesis at this point is like, OK, well, I can't remove elements from the list, so let's just turn the 42 to a 0 and see what happens. And it turns out, OK, that breaks the test case. So hypothesis, find me test cases smaller than this one we've currently found. Empty list, we've tried that. List containing 0, doesn't break. List containing 1, doesn't break. 0 and 0, good guess, doesn't break, right? So at this point, we've found that none of our alternate cases break the code, so we just return our current answer, which is 0, 1. Right, let's use our Python code, right? Let's tell hypothesis to shrink our test case down. And this is what it gives me. So, as you can see, the counterexample is 0, 0, 1, right? Which means that we probably just need to have 2 of something and then 1 of something to break my code. And as you can see, it fires an assertion error. OK, cool. So it found a test case, and this is, hopefully OK to debug with. So what was my buggy implementation, you might ask? Well, here it is. Basically, takes the list. If it's non-empty, it moves the first element of the list to the end of the list. Yeah, I never intended to code a reverse function. I just wanted something for this talk. But if you were given this on an exam and asked to provide a counterexample for why this isn't the reverse function, maybe something on the previous slide would be a counterexample that you provide. And in fact, this counterexample is the smallest, I think, which is really good, because our code found that purely through programmatic testing and through that greedy tree search algorithm. All right. Now, so far, I've introduced shrinking as kind of this black box where you just take a test case and it will just give you smaller test cases. However, not everything can be implemented perfectly. And so we probably need to actually figure out how shrinking works. So how do we even design a shrinker? Well, shrinking is automatically implemented by libraries for most common types. However, getting to know the underlying algorithm, as I said, it will help guide your decision on how best to use property-based testing. So how does one generate counterexamples? Let's do an example. Let's try and figure out a shrinking algorithm for integers, right? First of all, we need to ask ourselves, what is the simplest example of an integer that you can think of? 0. OK, let's ask ourselves another question. Given 2 integers, how should we determine if one is simpler than the other? Well, let's just say that if I was given 5 and 25, 5 is simpler than 25 because it's smaller. And if I was given -5 and 5, then 5 is simpler because it's positive. So we favor positive numbers, and we also favor numbers that are closer to 0. OK. Given these 2 ideas, we can create a possible algorithm. So suppose the integer to shrink is n, then we can generate these counterexamples. 0. We can halve n. If n is negative, we can turn it positive, or we can move it 1 space closer to 0. And if n is positive, then we can just move it 1 space closer to 0. So this algorithm isn't perfect, and most libraries use a more sophisticated method to generate counterexamples. However, it communicates the general idea of what we're trying to do here. So let's do a few other examples. Let's try and shrink a list of integers. Let's try and develop an algorithm for that. Well, first of all, what's the simplest example of a list of integers? The empty list. All right, so we try the empty list first. If that doesn't work, let's just take 1/2 of the list. So let's just try the left half or the right half. And if neither of those halves work, then we just try and remove a random element from the list, right? And if none of those work, well, we can't shrink our list any further. So let's just try shrinking one of the integers of our list. Here's another example, a binary search tree, right? And the algorithm is similar. So first of all, we take only the root node, because that's the simplest example. We could take only the left and right subtree. We could remove any one of the descendant subtrees, or we could shrink any one of the elements. Okay. Remember that our algorithm for actually finding the lowest possible test case, or the simplest possible test case, rather, is this kind of greedy tree search algorithm. And clearly, it can be improved, right? So again, all we have is an optimization problem. So we can apply similar optimization problem concepts to this problem. So here are a few improvements you can make. First of all, you can generate a few large failing cases before shrinking them in parallel. Once you find an unshrinkable test case, you can generate failing cases that are around the same size and try and shrink those instead. Or you could do small amounts of backtracking to see if you can find a better shrink. So all of these are ways you can improve the greedy hill climb algorithm to try and find the simplest possible test case. However, it must be noted that in most cases, the simple greedy hill climb will actually give you a counterexample small enough to work with. Now let's talk about test case generation, because once more, I've kind of treated it as a black box. However, sometimes when you do this kind of testing that is inherently random, you need to figure out, is the distribution of test cases really suitable to what you are testing? So as an example, let's try and test a dictionary, right? So we generate random lists of key value updates, and they're both strings. So I could get hypothesis to generate just a list of key value pairs of strings, right? And this was what it would look like. And okay, from the outside, it looks pretty strong, right? You have these unpredictable characters, you have these Unicode characters. It looks okay. However, what can we see about the distribution of this test data that maybe makes it not suitable for testing dictionaries? Well, we want to figure out what happens when there's a key value collision, right? Or when there's a key collision, rather. And if we're just generating random strings, it's going to be difficult to introduce non-trivial key collisions because you literally just need two randomly generated strings to be the exact same. And that is astronomically rare. So we want to alter the distribution of our test cases. And so how do we write a better generator to give the dictionary a suitable number of key value collisions? Well, here's a possible strategy. We could just create a random list of at least 5 strings and then just use that as our keys, right? And then for all of our queries, we pick only from that list of strings. And this would generate a suitable number of hash collisions. So how would I write this in Python? Well, something like this. So the implementation details are really just at the discretion of the library, so I'll go over them really quickly. So st.composite implies that it uses previous generators, or it uses library-provided generators to create kind of like a composite strategy. And so essentially, we take a random list of strings, we store them in keys, and we make sure that the length of keys is greater than or equal to 5. And if it is, then we generate a list of tuples where the keys are sampled from this list here, and the values are just random text. So this would be a better generator that generates a better distribution of data to test our dictionary with. Okay, now, we've talked about the algorithm. How do we write good properties? How do we use property-based testing well? So in truth, it's hard to come up with good properties to test your code. This property that I wrote earlier, it's kind of weak. It doesn't really specify the behavior of the reverse function very well. In fact, if I was just to give you this property and ask you to implement a function that satisfies it, what would be a function that satisfies it? Well, I could just take a list and just output the list again. And this would pass the property for like as many tests as I could give it. And clearly this doesn't implement reverse. So what do? Well, we need to write better properties. And summed up by John Hughes, there are several design patterns for writing properties that we can use. So the first type are invariant checks, or sanity checks. And so these commonly occur when you test data structures, in that you want to check that your data structure is well formed. Invariant checks are an easy entry-level check, right? That should basically never fail, because if they fail, your data structure is just completely useless, since it can't even maintain its own invariance. And so let's do an example. So I have a binary search tree here with a value stored and a left and right with either value none or a value pointing to another binary search tree. And then I have a function called insert, which allows me to insert an element into the binary search tree. And then a function called toList, which outputs the elements of the binary search tree in an in-order traversal. And then let's suppose that I made another composite generation strategy for generating binary search trees. This is just for writing tests later. Okay, so first of all, we need to write a function that actually checks if a binary search tree is well formed. And so it would look like this, right? If the left subtree of the binary search tree is not none, then we check if all the values are less than our value, or the value of our current node. And then we also recurse down to the left subtree to check if that is well formed. Then, if the right subtree is not well formed, we do the same, but we check if all the values in the right subtree are greater than our current value. And then we recurse down to the right subtree to check if that's well formed. Okay, so now we have this invariant checker. How can we use it? Well, here are two property-based tests that I can do. So the first one just generates a binary search tree. So it tells Hypothesis that I want a binary search tree. And then for each binary search tree that it generates, I want to check if it's well formed. So what this does, this might seem like a pretty redundant test, but it essentially allows us to test the generator and makes sure that whatever generator we're using, it's not generating invalid binary search trees. Let's also have another test here, which tests the insert operation, right? And essentially what we're testing here is after we insert a value into our binary search tree, is it still well formed? And so if the insertion preserves the well-formed property of the binary search tree, then the test passes. And we could implement one of these for every operation in our binary search tree. Okay, so that's invariant testing in a nutshell. There's also postcondition checks. And postcondition checks are kind of like a continuation where for functions or operations on data structures, what about the result or output of the function or output of the data structure is always true. So it's, like I said, it's like an extension of sanity checks, and we'll go into an example. So this is a postcondition check, which checks if a dictionary, after I store a key value pair into it, if I am able to find it again, right? That is a desired property in our dictionary, right? In that if we immediately store a key value pair into it, we should be able to look it up again under the same key. And so that would be a postcondition of the dictionary, in that if I insert a key value pair, it should still stay there until another query modifies it. Here's another example of a postcondition check, and this is one on a function. So essentially, let's say I have a GCD function that only works on positive integers for the sake of generating test cases. And I tell Hypothesis to generate two integers that are greater than 1, or greater than or equal to 1. And then for these two integers, I calculate the GCD of them with my function, and then I check if the output is actually a common factor, right? Because a postcondition, I guess, of the GCD function is that the output has to be actually a common factor of x and y. This doesn't guarantee that it outputs the greatest common factor, but it should be a sanity check. Now, let's move on to another form of property-based test, which is metamorphic properties. And what metamorphic properties are is that they are when testing functions, we want to kind of mess with the input a little bit and figure out what happens to the output. So it's kind of like calculus, where we mess with the input, we apply the function, and we see what happens to the output. So let's have an example. Let's say I have a list, I call it x's, and I reverse it, and I call it y's. So how is the result affected if I instead added an extra element to the front of x's before I reversed it? Now, this kind of specifying properties actually increases the number of possibilities for properties to write. Because you have all these interactions between different operations that we can encode into its own separate property. And it also increases the number of ways the counterexamples could pop up, because interactions means more coverage, means more places to uncover bugs. Okay, so let's demonstrate this previous property in a diagram. So I have my list x's, and I reverse it to get y's. But let's say I added an element to the front of x's to get x's prime, and then I reverse that to get y's prime. Now we just need to figure out what arrow do we add here from y's to y's prime to make sure that if I do this operation, if I go down this path and if I go down this path, the results are going to be the same. And it turns out that adding x to the front and reversing is the same as reversing and then adding x to the back. Right? So this is our metamorphic property, and it kind of looks like a commutative diagram. Okay, and the code to specify that property looks something like this. So we assert that applying the reverse function to a single element added to the front of x's is equal to reversing the list and then adding the single element to the end afterwards. Okay. Now, this property is much stronger than that double reverse property that we had earlier. And so here's a challenge for you. This property isn't perfect. However, we could easily break the previous property for defining reverse. We can break this property as well. So can you provide a terminating function on lists of integers that satisfies the above property but doesn't reverse the list? And I think this one's a pretty interesting problem. So we'll take a 1-minute break. Yeah, I hoped that I wouldn't be too slow to get through this part, but you're 60% of the way through. And if you have answers, I guess just put up your hand and somebody will come over with a microphone.
So yeah, just a function that takes off the first element from the list and puts it on the end.
A function that takes off the first element of the list and puts it on the end.
Yeah, that should pass that, right?
Let's think about this. So let's say I had the element, oh boy. Okay, doing this on stage is kind of hard. Okay, so let's say I had the element here. Let's say x was 0, and then x's is like 1, 2, right? Then reverse of 0, 1, 2 would give 1, 2, 0. And OK, now we look, reverse of 1, 2, because it takes the first element and puts it at the end, it gives 2, 1, right? And then this element is a 0. So 1, 2, 0 is not 2, 1, 0. But, you know.
Right, yeah, sorry, I slightly misunderstood. Sorry, yeah, I misread the code slightly, but yeah, that makes sense.
No, this is a really hard problem. I asked like 3 people, and only 1 person got it after my help.
Anyone else?
All right, we'll give it 10 more seconds. I'll give the answer at the end of the talk, don't worry. All right, let's continue. Answer will be at the end of the talk. So let's just talk about how we can come up with metamorphic properties, right? Because now we just have this kind of so many choices that we can use to come up with metamorphic properties. You might actually be paralyzed by the number of choices. So there are actually a couple of ideas in order to guide your reasoning to produce these properties. So the first one is there a way to mess with the input such that the output stays the same? So can you find some sort of idempotent structure within, I guess, the code you're writing? Is there a way to do 2 operations in a different order and end up with similar results? So this is the thing we did before, right, with reversing and adding to the front, except we added to the back at the end because the operation has to be slightly different to make sure they end up at the same place. And the third one is there a way to do an operation and then immediately undo that operation? Well, we saw this with reverse, right, and it wasn't very powerful in specifying it. But let's say that it was for, let's say that we were writing code to communicate over vast distances, and we needed an encode function and a decode function. then, since we have these two separate functions, we can tell hypothesis to just give me a random list of bits, I encode them, and then I decode them, and I check if that list is going to be equal to the original list of bits I started off with. So yeah, metamorphic properties can be weak by themselves, like that reverse function, but they can be very powerful when multiple are combined together. In fact, if we combine that double reverse function with the add to the front reverse is reverse add to the back property, then there would basically be no way to write a function that doesn't reverse the list. So if we just combined the two properties that we saw earlier, we would have specified the behavior for reverse entirely, which is incredibly powerful. So that brings me on to my next slide. Combining properties in this way can be so powerful as to specify the behavior for a function. And if we have enough properties that can directly describe the requirements of a function in all cases, then we have a specification. And a specification is kind of the holy grail, because essentially, any function that passes our tests basically is guaranteed to work 100% of the time. So let's revisit the oracle problem, because I actually omitted an alternate solution to this. And remember, the oracle problem is that even if we can generate large, random, high-quality test cases, how will we be able to tell if the code's output was correct? Well, in a lot of times, you're just implementing algorithms that are a more optimized version of less optimized algorithms. So what if we just checked our code against a simple implementation? Well, this brings us on to model-based testing. And in model-based testing, you have two things. You have a system, and you have a model. So the system is the code that you want to test, and the model is the code that describes what the system should do. So this kind of system model approach was actually developed a long time ago by Tony Hoare. And it basically, within it, the model is code that supports the same functionality as the system, except perhaps less efficient and less compliant. And okay, let's demonstrate it using a diagram again. So we have our system, and we have some sort of method or procedure to take everything inside the system, or to take all of the state inside the system, and abstract it down to a model, right, which is going to be our simpler version. We perform the same tests on the system and the model, and then afterwards, we check if, after we apply the same abstraction function to the system, after we perform the tests, are the two models still equivalent to each other? So this is kind of the similar commutative diagram kind of design pattern that we'll see a lot. So let's do an example. Suppose I had a data structure for storing a set of numbers, and it's implemented something like that, right? So we have a function inset that checks if the number is in the set. We have a function insert that checks adds the number to the set. And we have a function called remove that removes the number from the set if it exists, and it doesn't do anything if it doesn't exist. And then we have a function toList, which takes all the numbers in the set and converts it to a list and outputs that. So we'll actually be using a list of integers as our model to model our number set data structure. So first of all, we need to define two functions. We need to define a function to convert to the abstract representation or to the model, and we need to define a function to convert from the model to our number set. So the functions look something like this. So the first one, the abstraction function, takes in a number set and just uses the toList function to convert the number set to a list containing the numbers. And the second function, called refine, takes in a list of numbers, which is going to be our model, creates a new number set, and then just inserts all the numbers into the number set in order. And so, okay, from these two data structures, we now have a way to easily convert to and from the two representations. Now, we need to write some more code. So first of all, our data structure already implements a bunch of operations, right? But we haven't implemented the same operations on our model yet. So let's implement the equivalent operations. So we need an inset function, which is easy. We just check if the number is in the list. We need an insert function, which checks if the number is not in the list, and if the number is not in the list, we add it. And we need to implement a remove function, which checks if the number is in the list, and if the number is in the list, we remove it. Okay, so now that we have all of this backbone and we've defined our model, we need to figure out a generation strategy for our test cases and for our model. So first of all, let's generate our model. So what I'm going to use here is I'm actually going to use the refine function here to generate my model. So essentially, it takes a random list of integers, and it's going to use the refine function to convert that into a number set. And then that is going to be the output. That's going to be my randomly generated number set. And now that we have two models, or at the end, remember we will have two models, we would have to compare if they're equivalent. And so I guess in my case, my two lists are equivalent whenever they contain the same elements, right? So my implementation would look something like this, where I take two lists, model 1 and model 2. I check if every element in model 1 is in model 2, and if every element in model 2 is in model 1. And if either of those conditions are false, then we just return false. Otherwise, we return true. Okay. So let's define a few basic properties. First one, where we test the insert operation. So we get given a number set and an integer. And what we do is we immediately first convert the number set to a model. So this is the first step. We abstract the number set to a model. And then, to the number set, we insert the element x. And we do the same thing to the model using the model insert function. So we do model insert with the model and the integer that we're given. And then finally, we do the abstraction function on the number set, or the number set after we've inserted x into it. And then we check if the model output from that is equivalent to the model after we've applied our model insert function. And so this should always be satisfied. And so this is kind of, going back to the commutative diagram from before, this is what it looks like. Okay, and here's a second test that I could write, which is for remove, and it basically has the same structure. I take the number set, I immediately convert it to a model, I apply the same operations to the number set and the model, and then I abstract the number set, and I check if the two models produced are equivalent. Okay, perfect. Now we can test each operation in isolation. However, what if we wanted to test, what if we just wanted to throw a large number of test cases at our model and see if the output still somehow stays the same? Well, first of all, we need to generate some operations. So what I've done here is I essentially have a sort of enumeration type here in Python where my first value can be one of three strings: check, insert, and remove. And each one is indicative of a different operation that I have. And I also take an integer value that I draw, and it has a 50-50 chance of either being a small number or a number that's unbounded. And remember, I do this to alter the distribution of my test cases so that I'm able to, I guess, make sure that key value collisions, or the key collisions actually happen. And then finally, I return the update type in the first element of the tuple and the update value as the second element. Okay, and this is what the code for the final test looks like. So essentially, we take in our number set. Oh, by the way, this @settings thing is a way to tell Hypothesis to output every single test case that you're testing my code on so I can make sure that everything is being generated properly. And I was using it during debugging. I guess I never removed it. So I have my number set here. I immediately abstract it down to a model. And then for each operation, if it's check, I check if the outputs of inset are equal. If it's insert, I basically do the same thing that I showed you on that previous slide for insert. If it's remove, I do basically everything I showed you on the slide for remove. And then otherwise, well, we shouldn't really get here because we only have 3 values possible for the first position of our test case. Okay, and this basically allows us to just throw any cases that we want at our system and at our model, and then we can just immediately check if the system matches the model. Okay, so I've described to you 3 property design patterns, and you might be wondering, well, which one's the best? Which one performs better than the other? And well, we have this table here, kindly arranged by John Hughes. So essentially what he did was he implanted some bugs, some subtle, some obvious, into his code, and then he wrote properties to try and see if his property-based tests would catch the bugs. And this is the data that he gathered. So postcondition tests take an average of 77 test cases to find a failing case. Metamorphic tests take an average of 56 test cases, and model-based tests take an average of 5.8 test cases. So model-based tests basically blow the other two properties out of the water. And okay, well, you might be thinking, why can't I just use model-based testing for everything? And well, the slide is titled Pitfalls, so I guess you'll find out. Let's suppose that we were trying to use model-based testing for the myReverse function. I have my system, I have my myReverse, but what do I have as my model? I basically have to implement the reverse function again, right? And there's no simpler implementation for it. So I'd have to repeat my code. And repeating code is very bad. I'm sorry, Andrew Rice, I'm really sorry. And so there's no simpler way to implement the function that you're writing. However, remember that this is only a small section of property-based testing. We can use the other techniques instead. We can use metamorphic properties, which prove to be incredibly effective at defining reverse. Model-based testing can't solve everything. But when you have a simpler implementation, they can really do a lot. So let's zoom out, right? Property-based testing isn't going to be the only thing that is used on a project to ensure software safety. You could, for example, as I mentioned earlier, we could use a safe type system, or we could use formal verification. And now we'll discuss how property-based testing can complement these other methods really nicely. First of all, safe type systems. Many languages have type systems that can actually get rid of most of the bugs before they even get compiled, because their type system is very expressive and allows us to express guarantees statically very well. However, it can get difficult to encode all of your requirements in types without complex type hackery. Believe me. Okay, anyway, encoding some of the more complicated ones as property-based tests can greatly reduce complexity. And that is because you no longer have to do complicated type hackery. You can just write your guarantee as a property-based test. And so even though a property-based test is technically weaker than a static guarantee, it may cause less bugs in the long run because your type system is more simple. Okay, let's move on to formal verification. And what formal verification is essentially proving the correctness of your code with rigorous mathematics. And there are various means for you to do this. How to do it is outside the scope of this talk. And a lot of people have asked me this question. Why do I need property-based tests if I can just prove my program works? And they have a fair point. But like, what if your proof gets stuck? Is your program wrong? Is your proof just taking a long time to generate? Like, what's happening? Well, if your program's wrong, your proof just gets stuck, and you just have no idea why it gets stuck, and you have to find the counterexample yourself. So what property-based testing allows you to do is that it provides a good sanity check that the test case that you're writing, or I guess the formal verification that you're doing, will actually succeed. And so, property-based testing, since it basically checks your answer for you, it's a great preparatory step before formal verification. And it can even be used alongside formal verification if you, for example, write something that's obviously wrong. And let's zoom out even more, right? Because those previous two methods were static ways, or I guess white box ways, to make sure that your code is safe. And property-based testing is a black box testing method. It doesn't require access to the source code, right? And that presents many advantages in and of itself. So suppose that this was your system, right? And all of the system was your code. Then, in an ideal world, you could probably use formal verification to just completely prove that your code in your system works as intended, which is good, like happily ever after. However, most systems in real life aren't like this. Most systems are more like this, where you not only have your code, but you have a black box that you're kind of forced to interact with, and you can't really check if the black box is doing what it tells you that it does. You can only just trust it that it works. And this black box could take many forms. It could take the form of a closed source API, device firmware, or even device hardware implementation. And okay, what if we use property-based testing on it? Well, property-based testing doesn't care about if you have access to the source code or not. It can just test the entire thing. So property-based testing can test the whole system and even check for potential bugs from this black box, from code that we didn't even write, which gives you that extra guarantee that your code works as intended. Okay, that was a long talk, but let's wrap it up. So property-based testing presents many advantages. The code can be tested on large numbers of cases per second, which means that one property can actually replace many individual example tests. And you can also be continually running tests in the background because everything is automated. Property-based testing can also help people find problems they may have overlooked in their code and unit tests because everything is randomly generated. They're more helpful for debugging because it shrinks the test case down before it gives you the final counterexample. And they're more interesting to write because, and I think this point is very important, property-based tests force you to think about how your code behaves so that even when you're writing the test case, even when you're writing the property-based tests, you could discover that you didn't expect or you didn't account for the fact that your code could receive some random other input and behave in an unexpected way. And with property-based testing, since you're considering how a function behaves, you might be able to catch that rather than brainlessly typing down unit tests and just not thinking about the code that you're supposed to be checking. Okay, and these are my references. So the majority of my talk was sourced from these 3 papers. And if you want further resources, you can take your phone out, take a picture or whatever, I don't care. And yeah, there will be a link there, and there's just a link to a bunch of talks, including some topics that it didn't cover, like how you can property-based test on concurrent systems. Okay, so Q&A. Oh, also, I'll put up the challenge if anybody wants an answer. Okay.
Yeah, so can you just reverse the list and
Do you want to repeat that question?
Yeah, repeat.
Yeah, so could you just reverse the list and add something to the start?
Yeah, so essentially, the answer, if I go over here, is you just reverse the list, and then you prepend something to the front of the list. And okay, why does this code work? Well, this property-based test is actually just the inductive case for the reverse function, right? If you've, the people who've done Computer Science 1A, you may remember, you want to add, I guess you want to take the first item off the list and then add it to an accumulator. It's the same idea, right? So this is the inductive case. And we've done basically what every other computer program has done before, and we've forgotten the base case. So in the base case, we can literally do anything. So if I just give this code an empty list, this thing at the front could literally be anything. I could add 100 elements or 1,000 elements there, and it would still pass the property. Okay, so that's why our property fails. Here's an extra extension. Suppose the function reverse didn't just work with a list of integers. Suppose it was parametrically polymorphic. So in OCaml, suppose it was a function defined by a single rule that takes in a list of alpha and then outputs a list of alpha. Now, can you not implement the reverse function? Or are you forever tied to implementing the reverse function? Do you have an answer?
Anything that actually reverses it and then just arbitrarily changes every other element apart from the last element, right, will still work.
Okay, if you just arbitrarily change every other element, remember
I mean,
that like...
I meant as in, like, for example, duplicate every other element apart from the last one.
Duplicate every other element. Okay, let's think about this. So I'm going to give it the exact same test case. So let's say we have a 0, Wait, so it duplicates every other element. So like.
So
every odd
I
one?
mean, like, so say we had 0, 1, 2,
Yep.
it would reverse it, so we get 2, 1, 0, and then do 2, 2, 1, 1, 0.
Oh, so 2, 2, 1, 1, 0.
So,
Okay.
and then on the other side, my reverse would take 1, 2, reverse it, get.
2, 2, 1.
Oh, yeah. Oh, yeah, never mind.
And also demonstrates, like, all of these test cases are being broken on, like, x equals 0, x's equals 1, 2. Which means that, like, even if we test on very simple test cases, we might even be able to break our code. Okay, anyway,
I have a
continue.
question. Good talk. Can property-based testing test functions that use randomness?
Can property-based testing test functions that use randomness? Very good question. You need to provide the state in the property-based test. So essentially, you want to seed, you want to make sure that everything contained inside that test is pure. So you want to put the seed for the random number generator inside the property-based test and initialize the randomness in there. But otherwise, if it interacts with the environment, it might be more difficult.
Can this be used to test like statistical properties?
Can it be used to test statistical properties? I mean, it's really like any other mathematical method. So if the mathematicians haven't figured out a way, then I'd assume that this method wouldn't provide a breakthrough in that.
All right, thank you.
Hi, you mentioned shrinking test cases. So I might be working with some function where, say I'm working with Collard's conjecture and I want to work with powers of 2. In that case, if I subtracted it by 1, then I end up with a much more complicated test case. So you also mentioned that we can backtrack and choose a different method of shrinking. So when do I decide that I should use a different method?
Right, so if you're only generating powers of 2, then I guess like the space that you're generating is powers of 2, which I would represent, like, I would think of that as like a different data type to integer.
But I'm not just generating powers of 2, but
Oh.
like it's simpler to converge if I have a power of 2, so that would be a simpler test case.
Yeah, fair enough.
So in that case, if my way of shrinking is subtracting by 1, my test case actually becomes more complicated. So when do I decide that the way I'm shrinking is not right?
Yeah, okay, so I guess you really just have to look at how you consider simpler examples to be and decide how you want to shrink it. Because essentially, like, property-based testing is a design process, right? And you can, I guess, hack and modify any section of it to match your needs. And so if you wanted powers of 2 to be simpler, then I reckon you can just code that up. Yeah.
So thinking about the practicalities of using this method in industry, so obviously we mentioned like unit testing. It's can be quite time consuming and well, it's not very interesting to do. But the fact that this is requires a bit more thought, does that also provide for more complicated algorithms, for example, could it introduce quite a large overhead in the time that it would require to design the tests, essentially, especially if you're trying to discover properties which aren't very apparent in the first place?
Yeah, okay, so I think your question is, as the I guess algorithmic testing gets more complicated, would you have to spend more time developing tests? Is that right? So essentially, like, you definitely have to spend more thought on property-based tests. And I guess the trade-off of spending more thought on property-based tests is that the tests that you produce are stronger. And so property-based tests are like a great way, if you want to spend a little bit more time, to think about how your code works, to generate some really solid and strong testing software.
Thanks.
Yeah, so sort of the randomness aspect of this, one of the sort of practices that come with unit tests is every time you sort of do a commit or something in Git, you might run a unit test to see if it's broken anything. If this is being random, perhaps the previous time it was run, it didn't catch a bug that was introduced, and a new code commit is added. It doesn't actually break anything, but due to the random nature, it is detected this time. That could sort of cause confusion as to where issue occurred. Is there anything we can do here to sort of deal with this?
Yeah, if you just like 100% can't control the randomness and like your property tests just aren't pure and you just physically can't make it pure, there's an easy hack you can do, and it's just to run the test 1,000 times. And you can do it in parallel. It's trivially parallelizable. So for example, if you're like deploying it to a CI server or whatever, you can have like 10 clusters running like 100 tests each on your new code. So, yeah.
That's great if you're writing sort of small code base. I don't know if this is correct, but I think some of the unit tests for some of the .NET stuff take like a whole day to run. That might be wrong. But assuming really large sort of times to run these tests, you just saying run it 1,000 times is not really practical.
Yeah, I would say that it would take more computational resources to run, but then again, like it's just a trade-off, right?
You can just run the same test case on previous commits to see if it happens. Yeah, but still it's just small. So if it's taking more time to run the test, then you're going to have to go back and run the tree. No, but if you find it still in the test case, if you want to say receive the current commit for the previous one, you just run the same test case. Let's say that one test case takes an hour to run.
All right, for the people over Zoom, what they're talking about is essentially you could, once you find a failing case, you can compare it to previous commits, and you can like run it a bunch of times. And yeah, that's true. You could like design kind of sub-heuristics in order to like detect your bugs quicker. And yeah, since property-based testing is like a design pattern, it's not like a fully fledged algorithm, you can do all this stuff, and it's all fair game.
Thanks, Janan. A great talk. Now that we know of a simple way of generating test cases, hopefully some of us will test our code. Next up, we have Gabor, and he'll be talking about AI safety.